Good afternoon, everyone. So today we're gonna move on from some of the methods that we've been talking about and looking at sort of building up intuition on sort of actual systems level models. Okay, and so specifically thinking about energy. So if you guys recall, this particular sort of diagram is a sort of high-level architecture of our energy system that we've showed kind of at the beginning of class. And so a lot of what we were talking about before are specific sort of technologies and how they work, and then sort of building some expertise and intuition on some of the modeling approaches that sort of connect these. But now we're going to take a step back and start looking at a couple of examples of actual sort of systems level models. Okay? And so the first thing we are going to start with are more sort of simple decomposition models. Okay? So these are a way for folks to think about this at kind of the highest level. So Kaya, has anyone heard of the Kaya approach before? No. All right. So this was initially developed as a way to understand drivers for greenhouse gas emissions. So I'll ask you guys a question. So what are some choices and decisions that may influence the way that you use energy or that may affect your carbon footprints? Anyone have any ideas? Yeah.
Vehicle ownership.
Vehicle ownership. Okay, and so if you own a car and you're driving around, ostensibly that particular type of activity leads to more emissions. Yeah. Heating and cooling, right? And so how much AC and heating use, that actually has a pretty significant impact on like your electricity consumption. Anyone else?
Like to travel.
Yeah, if you like to travel, right? So if you're talking about like flying, that's one of the big ones. They say there's like a handful of levers in terms of ways that you can mitigate like personal emissions, and flying is, they say, is like equivalent of going vegetarian, I guess, right? So that's another one, right? Diet choice. Okay, so all of these things are particular activities that you partake in that can influence greenhouse gas emissions. But if we're to kind of back out a little bit and think about this at the sort of population scale, so most of the things that you guys were just mentioning here are mainly having to do with sort of the activity and consumption piece of it, right? And so the amount that I drive or fly, my diet choice has some influence, right? That's a consumption-based activity. Transportation mode. So all of those kind of fall into activity and consumption, and that's one of the areas that you personally may be able to influence, energy and emissions intensity as a whole. But the way that we might sort of measure this is all of those things that people do and goods that they consume, right? That's just one piece of the pie. We also need to know how many people consume those things or partake in particular activities. And then we have to know the general sort of energy intensity of any particular activity, and then the carbon intensity associated with that particular energy use. Okay, and so there are other pieces of the pie that do have an influence for greenhouse gas emissions. So this is energy intensity, for example, would be where efficiency would really make a big difference, and then carbon intensity, depending on the fuel consumption, can make a difference as well. So the Kaya identity is a form of decomposition where we're essentially just sort of multiplying these things together. So all of those factors, those are the sort of things that determine the final product of greenhouse gas emissions. So this is, I think, one of the simplest frameworks that we can use to understand what the drivers of changes there are in emissions, or like where we can leverage specific things, right? And so when I was asking you guys about what activities you partake in, right, that is changing the activity lever. We could, in theory, like cull the population. That's probably not the most popular activity, right? But that would reduce GHGs. You could also make things more efficient, and you can make things cleaner. But those, in totality, kind of represent the possible things that we could do. So generically, like, yes, we could like track individual activities and that sort of thing, but the Kaya identity was originally derived as more of like a holistic, high-level a greenhouse gas tracker. And so the way that they think about activity is basically the amount of GDP produced per capita, and then energy intensity is represented by the total amount of energy per economic activity, so GDP, and then carbon intensity is how much emissions associated with consumption of some amount of energy, right? And so these are all average numbers, but I can use this and sort of multiply across, right? The population will cancel with the per capita, the GDP cancels, the energy cancels, and then you're left with greenhouse gases at the end. Okay? Any questions about this? Yeah, so again, very easy way for us to track, but I think this framework is very useful for us to understand. Basically, you're like doing these unit canceling things, right? And that's essentially a lot of energy systems models are sort of more detailed representations of these, where we're doing more of these unit cancellation things, but for specific items, to go from kind of beginning to end stage of things where you have input data and then outputs of interest. Yeah, and so this particular identity equation is actually derived from an earlier decomposition method called IPAT. Has anyone heard of IPAT? Okay, cool. So that's the one that folks are maybe sometimes more familiar with. So this is an equation derived in the early 1970s by Ehrlich and Holdren. That's the famous John Holdren, who was like science policy advisor to the president a little while ago. But yeah, so they instead of this Kaya identity, this IPAT decomposition looks at not greenhouse gas emissions, but actually local air pollutants, and how that relates to sort of population, affluence, and technology. And so the IPAT comes from this impact equals those things. So population, affluence is essentially like our activity thing. And then the technology is kind of the combination of both the energy and the carbon intensity from the Kaya equation. A lot of people kind of appreciate breaking down this technology piece into the energy consumption piece and the emissions accounting piece, because then you can more explicitly try to represent things like efficiency as its own sort of influential lever, right? Okay, so same type of approach to illustrate how different elements contribute to environmental problems, right? Specifically with pollution. And again, that lets us focus at a high level what needs to be changed, right? So we're going to be focusing on population and consumption. And actually, one of the things about the IPAT equation is that in the way that it's formulated, a lot of people essentially viewed technology as the problem, right? This is the source of our environmental damage and pollution. And so if you can get better technology, you can enable a lowering of pollution. And so I think the bigger difference with IPAT and Kaya is that in the Kaya one, right, as I was mentioning, the viewpoints change so that all of the levers besides, I guess, population, although maybe population still plays somewhat of a role, are all sort of equally considered important parts of the solution. Questions? All right. So population and activity are considered socioeconomic parameters. GDP per capita is a general measure of economic activity, but not necessarily of well-being. And so again, this is because it's such a sort of high-level equation, right? It doesn't have some of the nuance that you might want to bake into kind of an energy system model, but it's acts at least as a starting point and to get you guys thinking about, drawbacks of this particular type of identity and whether or not it can be improved. So the energy intensity and carbon intensity are more sort of socio-technological parameters. And I call it sort of socio-technological as opposed to just technology, because then it incorporates, the aspects of society that can influence these particular parameters. So energy intensity depends on the type of consumption and production and the energy technologies that are being used. And then carbon intensity depends mainly on the energy resources that are being used, right? So there's some question, right, of if you want to lower emissions, are we doing it through activity and consumption? Are we doing it through improving efficiency and energy conservation? Or are we doing it through sort of fuel switching, right? And I think one of the nice things about looking at things at the system level is a lot of times people come into like a program like EGG or TTP, just as examples, where you have a particular interest or focus on some technology, right? But I think getting exposed to the fact that that's only one piece of the lever, there are many different solutions, it's important to keep your mind open about these things. So there's a bunch of simple calculators that you can use. We talked about doing forecasts, right? And so the Kaya identity is like one of the easiest things that you could essentially forecast. You can have extrapolations for each of those parameters and just kind of see what that would do to your total emissions, right? And so you can have specific forecasts for what the population is doing, what the economic output looks like, and make assumptions about how energy and carbon intensity are either increasing or decreasing, and see what ends up happening in terms of emissions, right? And so I put a little website here that you can look at if you wanted to do, a more sort of in-depth playing around with the Kaya model. And then the sort of last thing I'll say about it is that, right, the Kaya model, this identity is pretty simple, right? And so you can think about sort of breaking down specific assumptions of the Kaya identity to make a more complicated system model. The other thing is you can start thinking about breaking these things down spatially and temporally as well. And so the temporal part we've talked about, that can let you make these forecasts, but actually you can do regional disaggregation, which is what's being shown in this particular paper, where they looked at a bunch of different countries and applied different parameters from the Kaya identity to look at things like how emissions would change. Okay. So that is our sort of simple look. No questions about that. All right. So now let's talk a little bit more generically in terms of the framework of how we would go about sort of developing some of these system models with those kind of relationships in mind that we're learning from these like Kaya and IPAT type identity equations. So there's a lot that you could cover in a system model, and I think one of the first important things to think about is the scoping of your model, right? And so what is it that you actually want to examine? And that can actually inform a lot about the sort of design approach, or the design of your model and the structure of your model. And so am I thinking about like optimizing some kind of systems operation? Am I thinking about how technologies are entering and exiting the market, how they're changing over time? Do I care more about sort of how behavior may relate to my sort of energy system? Do I care about the sort of economic piece of it? Am I looking at infrastructure deployment, right? And so these, whatever sort of decision you're trying to identify as an output of your model is going to help inform, what and how you're scoping the model for. Regional coverage of your model, that can be really important, and not only what you're covering, but to kind of what resolution, right? And so you may say, oh, I'm interested in like a California-based model or a US-based model or an international model. But that could mean a lot of different things if you are looking at things, at a city level versus a county level versus a state level, right? And so the resolution of your spatial coverage matters as well. Yeah, and then how far into the future will your model cover? Are you just doing a retrospective look? Are you looking at sort of short-term, near-term impacts into the future? Or are you doing years-long, decades-long examinations? And the type of model can have really big impacts on what the outcomes will look like relative to kind of that time span that your model is covering. Okay, we'll also talk now about sort of these top-down versus bottom-up models. And so a top-down model is one that focuses more on understanding macro trends or relationships that describe kind of the overall system, whereas bottom-up models focus on specific pieces of the system and then kind of build up to describe the system as a whole. So let me ask you guys, is the Kaya equation a top-down or bottom-up model, and why? Yeah, top-down. Right, so focusing on macro trends. And what if I started getting into, let's see, let me jump back to this identity model. So we were talking about like activity, right? What if I started getting into specific activities, like where you guys were talking about specific travel choices or dietary choices, and I broke this down into like 50 different activities. Would this still be a top-down or would it be a bottom-up model?
More top down now.
Yeah, so I guess the point that I'm trying to make here is that oftentimes we delineate these things as kind of top down or bottom up, but there is some kind of gray area where you are thinking about constituent parts, but then describing some of the relationships that make it into sort of macro trends. So yeah, I mean, even I'm going to be sort of generally characterizing models as kind of top down or bottom up, but just know that there is some kind of like hybridization. It's not always super clear when you think about particular elements of a model, because it could have many top-down elements, but then rely on pieces that would look like a bottom-up model, and vice versa. Okay. So in general, we're going to talk about some of these more top-down type models. We're going to look at some econometric models, some input-output models, some CGE models, computable general equilibrium models, and then system dynamic models. And then on the sort of flip side, we're going to look at some bottom-up models as well, thinking about sort of partial equilibrium, optimization models, simulation models, and multi-agent models. All right. So, first thing we'll talk about with top-down models, we're going to kind of just go in order of the things that I was just mentioning. So, econometric system models. A lot of these are a little bit more open-ended, growth-driven models. So econometric models, by virtue of them being an econometric model, right, is more heavily reliant on data. You can't actually sort of construct these models without calibrating the parameters based on things that you're actually viewing in the past. And so that can actually be a pretty big barrier in instances where the data, the access to that data doesn't actually exist. That can be particularly problematic. I'm sort of explicitly talking about this here when you're looking at sort of different regions. And so if you had some kind of system model, econometric-based system model that's looking at a particular country, and you're using like databases to identify and look at specific data from those databases, if you try to replicate the same model in a different country, you may find that like that data doesn't exist, or is like in a slightly different form or format where you're doing sort of an apples to oranges comparison between different variables. That's a common problem that you may experience with this type of approach. So probably a more important caveat is that oftentimes these sort of larger system models will ignore the structure of the energy demand. And so that's what I would actually characterize as a like quintessential element of the sort of top-downness approach here. So you assume a particular type of sort of structure in an econometric system model, which is basically that the past will kind of look like the future, right? And so if I were to go back 10 years and build an econometric system model for like gasoline consumption in the US, right? You'd have many years of data to calibrate on based on how like population is changing and even like how fuel efficiency is changing, right? But you might miss out on like a growth of a new technology, so something like electric vehicles, which may have been a lot less, 10, 15 years ago, that's sort of structurally changing our energy demands, in particular, right, with gasoline. So it's often not possible, or at least very difficult, for econometric system models, which are calibrated on past data, to like keep pace with more revolutionary things that might be happening in the system. Yeah.
So you wouldn't say you're developing a model, but like there's an event that shouldn't be in the scope of your model. You can't really exclude that from your model. So I'm thinking of like flights and COVID when that hit.
Yeah.
There's no way that a model is going to be able to predict that that type of impact would have happened, but you don't want that to skew your data of your model. So
yeah, I mean, COVID is a really good example, right? So there's no way to represent something like that happening in this type of model, right? Unless you are observing some kind of pandemic and its effect, and then you wanted to then replicate it again. Yeah. With a bottom-up model, you could, in theory, try and bake in something like that, and then you could make some assumptions that it might happen again or something. But without prior data on it in an econometric setting, top-down setting, you wouldn't be able to. Yeah.
And you wouldn't want it to?
Well, maybe. It depends. That's a more sort of philosophical question about what you're trying to get out of your modeling, as opposed to yeah.
Scope thing though, because you would only want that.
Yeah. Yeah, that's right. And so if the focus of your project is understanding the effect of pandemics on energy consumption, right? Yes, then you've decided on a scope that's wants to focus on those things. But yeah, you would think about these things mainly in the scope. Yeah. Typically, you're not going to have assumptions of equilibrium, and our parameters are kind of one-sided and unidirectional, and so as things kind of change, there's a corresponding response, but not in a really endogenous way. Yeah, and there's an example of an econometric system model, so E3, ME model. There's a systems model that we'll look at in just a second. Right, so a really simple example of an econometric system model that's looking at total energy demand might look something like this. I have some kind of coefficient, and then I'm multiplying income times some elasticity, multiplying energy prices and some price elasticity. And basically this is saying, if you make some amount of money, and energy prices are a particular level, I can look at historical data to essentially understand the relationship between those variables and my total sort of energy consumption. And so, this is a simple regression where I am essentially calculating the value of several parameters calibrated to historical data to create this, simple model that describes energy consumption. So your A, your alpha, and your beta are all going to be estimated based on historical data that will then give us insight into energy consumption. Okay. Any questions about this? Okay, so it doesn't always have to be all that sort of super simple, right? There are larger system models that whose a lot of the basis of many of these models are essentially broken down into sort of sets of like econometric regression models. And so the one that I'm kind of showing here, this is a model developed by E3, which is a like consulting company, think tank based in San Francisco. They've done a lot of work for the state of California, like ARB and CEC. And so this is one of their systems models that's looking at the electricity system, our economic system, and the climate system. And a lot of the outputs that are sort of generated from here are essentially derived from sort of econometric regressions. And so these outputs based on things like how CO2 pricing can affect a bunch of things like employment, GDP, consumption activity, and so on. And so kind of at the end of the day, a lot of this is broken down into a whole series of sort of simple regression models.
Are they isolated? Each one's isolated regression?
Many of these are. So the way that I would kind of describe this model is if you were to do something similar to the Kaya identity where you're decomposing specific elements, you can calibrate those elements to be based on parameters that are historically calculated. And so that's the sort of econometric piece of it. Okay, so that is a sort of build up to get some understanding of econometric models. The next example that we're going to look at are, or is known as input-output. So this is a particular type of problem. So this was developed by this guy, Leontief, who won the Nobel Prize back in the 1970s. Originally used to help planning for, during like wartime. I guess the example was specifically about producing tanks, but actually is now used as a pretty popular type of model for assessing environmental impacts of manufacturing. And so the way this works is it quantifies sort of interrelationships amongst different sectors within an economic system. And that's nice for understanding system level impacts, because a lot of these things are like correlated with each other and have systemic downstream impacts. Okay, so what we'll actually do is we're going to do a little example here. I'm going to give you guys a second to see if you can work this out. You have 4 producers here. Someone who produces soda, someone who produces cans, someone who produces aluminum, and someone who produces water through a water treatment plant. So everyone get out a piece of paper. And the goal is to calculate how much each industry produces in order to make 1 million cans of soda. And then we're going to use this a cutoff rule that you continue to place orders until you request less than 1 unit. Okay, so just to get us started, right, million soda cans. So to make 1,000,000 soda cans, I need 1 gallon of water for every 10 cans of soda, and I need 1 empty can for every can of soda. So to make 1,000,000 soda cans, I also need 100,000 gallons of water, and I need 1,000,000 empty cans. In order to make 100,000 gallons of water, I need 100,000 divided by 1,000, so I need 5,000 pounds of aluminum, and I also need some cans of soda. Don't ask me why, that's just how the problem's set up. And then for cans, I need 1,000,000 cans, so I need 1,000,000 divided by 32 pounds of aluminum, and then I need 1,000,000 divided by 1,000 times 5 gallons of water for each one. So see if you can calculate how much each industry produces to make 1,000,000 soda cans. So I'm gonna give everyone we'll do 5 minutes, and then I'm gonna calculate along with you guys as well on my iPad here. All right, is anyone done? Anyone think they have the right answer? I'll give you guys another minute or so. If you get the right answer, I'll give you an extra point on the homework. Motivation. All right. Anyone want to volunteer an answer? Yeah, I know.
No.
Any ideas? No, okay. Why is this not showing up? Hang on. Okay. All right, give me 1 second. Okay, we're having some technical issues for some reason. I don't know why my thing decides to not mirror anymore. Okay, let's see. Okay. Dang it. All right, so I don't know why this isn't working, but that's all right. We'll just do it like this. Okay. Here's a marker today. So the basic idea is I have some starting point, 1 million units of soda. And so what do I need for this? I need some amount of cans and some amount of water. So I need 1 million cans and then 100,000 units of water. Okay, and from here, I need some amount of water and some amount of aluminum. and so on. So 25 units of aluminum, 2.5 sodas. This needs 39.5 of water. 12.5 cans. Okay, and so basically you're continuing to do this up until you have less than 1 unit, right? That's when we do our cutoff rule. So here we're gonna end. Here we also will end. Here one of them ends, but the other one, 2.5 cans. And then we end here. And so on and so forth. And this can take a little while, right? And so, did anyone end up with this? You know, this is only about a third of what we need, but if you kind of continue down this chain for all of the demands and how they translate into particular sort of products, you end up with 1,078 cans of soda. You get 156,508 units of water, or gallons of water. 1,016,349 cans, empty cans, and then you need 32,543 pounds of aluminum. Okay, who got this answer? No one. All right. Yeah, so because of the interrelationships between different parts of your sort of supply economy, doing this type of calculation can be pretty rough or sort of time intensive, right? And in reality, right, this is a pretty sort of contrived example. In reality, it could be even a lot more sort of complicated. And the idea is that you have some sorts of, the reason why we call this sort of input-output models is we have, right, essentially these demands of inputs that lead to kind of the outputs of essentially what's needed. So it turns out this dude, Leontief, he actually won, so part of his Nobel Prize has to do with kind of the development of a particular type of approach to deal with these sort of input-output models, right? So let's talk about how you might actually build a representation of this that's going to let us do these sort of models in a lot simpler of a way. So we form what's known as an input-output transactions table, which represents the flow of purchases between sectors, which is exactly kind of these arrows, right? So oftentimes you're constructing a make table and a use table, which shows which industries make which commodities, and then the use table part of it shows which industries use which commodities. And we actually, in some forms of these input outputs, combine them to form a whole sort of matrix that represents the entire economy. Okay. So in a simple two-process example, we have Aij, which represents how you use a material for a process. So I is the source and J is the process that uses the material. And so if I want to produce some kind of process, I, then my yi output is going to tell me the sort of demand of all of the materials inputted needed to produce that particular process or good. So we can build this up represented in our transactions matrix. So at the 0th level, you have I times y equals y. That just tells us what we need for our first demand, right? So I need 1 million sodas, so that's basically what I need. At the first level, you're looking at the first tier, where you're basically saying my transactions needed for that particular output, right? And so for 1 million sodas, the first level would tell me I need 1 million cans and I need 100,000 units of water. And then in each successive level, you're basically looking at the requirements at every tier kind of down our list. And so in totality, you would have something like x is equal to I plus, so I being the first thing that you need, the 1 million sodas, plus the thing that you need beyond that, right? A plus AA plus A times A, and so on and so forth. And that will give you a vector of your final demand. So if I were to do this in a 2-process example, so we have our transaction matrix where we're looking across rows to show us use of row process outputs in other processes. And then the columns show you the inputs needed for those column processes. Okay, and we can actually simplify the whole sort of transactions in this manner. Okay, so this might look a little bit straightforward, or less than straightforward, but let me show how we can apply this to our particular example. Okay, so if we're gonna look at our soda example, and actually I'll just go back to this guy, so we have the numbers to look at. Okay, so we're gonna build our transactions table, which we'll call A, and that's equal to a large matrix, and I'm gonna write soda, water, cans, and aluminum. And I'm gonna do the same in the columns. Soda, water, cans, and aluminum. Okay. How much soda do we need to produce soda? I think I heard it. 0. Okay. And then how much water is needed to produce 1 can of soda? 1/10 of a gallon. So 1/10. What cans do we need? 1, right? And 0 aluminum, right? And so this is the way that we fill it out. We're going down by columns to indicate the need to produce any sort of individual product or process. So here, how much for water, right, our relationship is you get 5 per 100,000, 10,000. Yes. You don't need any water to water. You don't need cans for water. Aluminum, we need 5 out of 1,000 cans. So same process here. 1 over 32. 0. 1.58. 1 over 2. Okay. So this is our transaction matrix, right, based on this particular example. What is our y equal to? So we're gonna have soda, water, cans, aluminum. What do we want? What's our end goal? 1 million cans of soda, right? So we'll do something like this, 0, 0, 0. Okay, and all we need to do is x I minus a inverse times y. And if you solve for x, you can just plug this in. You'll get 1,078.25, 156,508.27, 1,6,349.99, and 325. Okay, so this is our soda, water, cans, and aluminum. Okay, so you can see in this way creating the transactions and then just doing this process, which is the sort of simplified form of, doing a infinite sum of your transactions tables multiplied. This will give us the same answer as if we were to sort of manually sort of calculate this out, right? Except that this process can be expanded to much more complicated IO tables and still be sort of trivial to solve. As opposed to this, we're already kind of, getting pretty manually intensive or labor intensive to solve sort of manually. And in fact, this answer will be also more precise than our rule where we were doing this like cutoff thing, right? Because this is actually giving us the true requirements for the full set of transactions. Okay. Any questions about this? Yeah.
What is I?
I is, here, this is the identity matrix. Yeah. So that is in reference to when I do this thing, essentially the I in each level is saying at the very beginning, the thing that I need is 1 million cans of soda. So you do I times Y. So if you don't know, if you're unfamiliar with matrices, the identity matrix is 1, 1, 1, 1 down the diagonal. And so you have, when you multiply the identity matrix against Y, it'll just return the same thing, 1,000,000. So you would essentially be doing what you're seeing here in this supply chain buildup. Each level will look something like this. It will look like 1,000,000 0 0 0 plus, and the first term is going to be a times y. So this is going to give us, if I multiply our y, which is this, times this transaction table once, it will give us 0, 100,000, 1,000,000 for cans, and then 0. This is our first level. Plus, and then our second level will be these things plus whatever things come out of here. And this term, I minus a minus 1 times y, is a way to simplify this final expression here, this total. It's the shortcut. We're not gonna derive it. I guess it's not that hard to derive, but yeah. So this is essentially this sort of level products, a process, adding them up to sum up to this thing here. And then, did you have
I was
a
going to ask
question?
about the identity.
Okay, yes. Any other questions? So in energy systems, these input-output matrices are a really powerful way of being able to there's a powerful way of reducing the sort of computation needed and simplifying it into a pretty straightforward process, so that when I have more complicated input-output tables, you can really quickly be able to understand the sort of initial demands or the total demands matrix, right? And this will sort of pretty accurately capture the sort of interrelationships between all of the different sectors and be able to reduce that down to some needs matrix based on a particular output that you're interested in. And so if you wanted to look at like the manufacturing of an EV battery, you can see basically all of the pieces that are needed from that, and actually there's ways of extracting like how different sectors will contribute to that. All right, questions? Okay, let's take a quick 5-minute break and then we'll jump back into this. Yeah.
Questions on today. In reference to this one, viability of where it becomes more attractive, or any of these,
Yes.
are you talking about like each one individually, becoming more attractive compared to what it was previously, or in reference to compared to one another to each of the resources?
That is deliberately left ambiguous as a way of
Measuring how we see it.
Yes,
Okay.
exactly.
So you said that there is like the equation is 5 plus 3.6 times the correct answers percentage.
Yeah.
And does it mean that for each question there's only one correct answer?
Yes.
And,
Maybe.
But what if the other question? But if the other answers are kind of worded ambiguously, so that they could also be right.
That's part of the point, is that it's ambiguous.
So like.
Also, everyone, just to make clear, you cannot have your probabilities add up to more than 1 on any problem.
So what would you do if one of them added like higher than 1?
In all the answers.
Yeah, I mean, I guess that's only really relevant if you put more than 1 on the correct answer. Otherwise, it's going to penalize you even more. Yeah.
What if I'm just bad at math?
Yeah.
You get penalized for being bad at math.
Yeah, and then
Yeah.
it will instantly become a negative infinite.
Yes.
So
Yep.
like you recommend the approach of even if like we give maybe 90% to the correct answer, we should still assign small percentage to all the other answers just to be safe.
Well, that's up to you, how safe you want to be on the homework. Yeah.
Okay.
Yeah.
Well, that makes sense.
Yeah.
For this particular assignment, homework number 2, you don't want us to submit the works, right?
No, you
should.
should.
The assignment with probabilities and that's it.
No, well, you should submit everything. Yes.
Works?
Yes.
Okay.
Yeah.
Oh, really?
Yes.
Oh.
You can you can still resubmit. Yeah.
Okay, well, though.
Just do it on paper and don't have the paper anymore necessarily.
Oh, well, it's I guess it's fine, but we would prefer
But
that
I
we
mean,
see
if
your work.
just the percentage is graded anyways, like why? Like what's the point of uploading the other stuff? Like, or do I get extra points for it? Like,
I guess I don't know. It's like to prevent cheating, I guess, but it's fine. Yeah.
okay.
Yeah.
I mean, I could go back and do it.
No, it's okay. If you have it, I didn't make that explicit. If you have it, I would prefer that you submit it, but if not, it's okay. Okay, let's move on. Yeah, if we have questions about homework, we can chat afterwards. Okay, so the input-output model is useful in particular sort of sectors and understanding demand, like this type of thing, for a subset of problems. I think where it gets particularly interesting is there was actually a sort of derivation or sort of built off of the traditional Leontief input-output approach here, is thinking about computable general equilibrium models. Okay, and so this is, I would probably argue, sort of a little bit more widely used than than your sort of traditional I/O models, and they have a sort of bigger emphasis on prices. And so a lot of economists kind of took this I/O thing and kind of ran with it with a particular focus on aspects that they were interested in. So thinking about things like wages and labor demands and prices and that sort of thing. And so what they did was to expand the input-output model to include, into something that's known as a social accounting matrix, or a SAM, which represents benchmark data in equilibrium. And so it's essentially your input-output model with a few things kind of tacked into it that represent sort of equilibrium conditions. Okay, and so this is a generic CGE social accounting matrix that I'm kind of showing over here. And I just kind of want to demonstrate for illustrative purposes essentially what's changed. Okay, and so this is our input-output matrix. That's our transactions matrix that we were talking about, the A, that relates different sectors of the economy with one another. And so, you know, if I were to produce something from a particular thing like item 4, you know, that might be representing, I don't know, like oil, the oil industry, right? If you wanted to have some change in like gasoline demand, and then that would trickle out to everything else, right, in the way that we've seen here. But in addition to that, they have added a demand matrix that talks about consumption and then like other portions of demand. They've added this economic piece which relates all of these sectors to their corresponding labor, capital, and energy usage. And then they have some of them, not all of them, will have a piece that connects like taxes and tariffs that relate to any particular sector as well. Okay, and so you can think of these sort of additions as telling us not only about the individual demands into each sector, but also how they affect things like labor, capital, and energy usage, and like tax revenues. So these computable general equilibriums, they can also help understand with, they can help you understand the effects of things like policy interventions on like the broader economy and different sectors. And so one really common or obvious, I should say, area of intervention that they were particularly interested in looking at is something like introducing a carbon tax, right? And so I can take that, directly kind of manipulate different sectors that would get affected by a carbon tax, and then see how that trickles out across your full economy, right? And so this would be difficult to do in isolation, where if I had a carbon tax and I wanted to look at a particular sector, you could go in and do that, but then remember all the like downstream effects of that would be hard to like propagate back through. Yeah.
I'm wondering like how well can you do like predictions for the future, because like these tables are quite static, right? And like things might, like some of the entries in the table might change significantly in the future. Like if you, for example, just change the text summary, you kind of assume that everything else will stay exactly the same, right?
Yes, exactly. So a lot of the calibrated values are based on equilibrium conditions. And so the idea with this is it will tell you how the system responds kind of on the margin for the first like transactions thing. But actually, the beauty of the input-output piece of it is that if we assume that like the demands and prices are like functionally correct based on what you've seen historically, like this changes prices and will have a trickle-down effect throughout all of the sectors. So you're recomputing a new equilibrium. And so what you're saying kind of applies for every like level of A, but kind of the idea is that technically this should be able to consider how prices will affect other things in a way that you go back to a new equilibrium. It's one of the reasons why the IO table in isolation, the original transactions table, I think would be more vulnerable to that type of thing. Whereas in a CGE, technically you've designed it in a way that you're like recalculating a new equilibrium because you're including like demands and prices. Yeah. Okay, the last example that I'm going to give for our top-down models are our system dynamic models. So this explains behavior of systems from a series of different interdependencies, and also considering how those dynamics may change over time. So you may have something like this, where you have different dependencies between different things, except that essentially what's being added is that you have like a little t-index here, where your requirements and your demands may actually be changing over time. And so if you do that, you can no longer have this type of simplification, or at least not that I'm aware of, that anyone has figured out. And rather than solving this analytical solution that I'm providing, you have these larger system models that have these feedback systems or loops that essentially you can calculate pieces of them in an analytical way. Okay, so here is an example where we're looking at sort of adoption of a new technology. So you have potential adopters becoming adopters, and then this kind of breaks it down. So this is actually a systems dynamic approach of the Bass diffusion model that we talked about before, where they're dynamically changing some of these attributes about the innovators and the imitators, and the sort of mechanism with which this happens, right? And so, yeah, this is a particular, this is a way to show the Bass diffusion model happening sort of dynamically with a sort of fixed P and Q that you could actually modify in a systems dynamics example to make the curve do any sort of thing that you're interested in. And it can get really quite complicated, right? So this is a simple example of the Bass diffusion curve. But if you're talking about modeling the entire sort of energy economy, you can imagine that a lot of these things, so this is like a sort of systems diagram model for these types of system dynamics that was used in a particular paper. But this gives you hopefully at least some sense of the sort of complexity behind behind this. And the way that we think about breaking these down is looking at sort of particular, essentially chunks of the model, and then modeling the sort of interdependencies that arise in your, in the dynamics piece of it. So there are pieces of it that you have a particular idea about what the dynamics look like over time, then you're sort of individually sort of modeling these. So this piece can get pretty complex pretty quickly, and you need a good deal of computational power to be able to do this to a degree of complexity. Okay, any questions about that? Yeah, so I would say kind of the evolution of IO to CGE, that has been sort of pretty well developed. The systems dynamics models come from, I would say, a sort of different stream of like engineering that kind of led to these larger system models. So they're not built off one another, they're more sort of complementary. Okay, so that's our top-down model. So now we're going to talk about our bottom-up models, where rather than thinking about breaking down, starting at the sort of systems level and then breaking down pieces of it, we're taking pieces of known parts of the system and compiling it together into maybe a larger system. So the first one we'll talk about, which is kind of in direct contrast to the computable general equilibrium, is a partial equilibrium model, where we are assessing only sort of a single or subset of sectors. So here you might get a lot more detail about a particular technology of interest or a particular subset or a sector of interest. And the trade-off is kind of understanding the relationships that you might have with the broader economy, right? And so an example of this might be, so like a project I did in grad school where we were looking at how car companies would respond to particular types of regulation. And so we would build these models where, very complex models, where you estimate this, like you model the decision-making process of a particular car company in a lot of detail, because they make lots of choices about what kinds of technologies they would implement in a car. And then you could eventually look at all those decisions and then compute over the lifetime of vehicles, like how much energy they would consume, how much emissions they would lead to, right? And so that's a whole bunch of detail into a particular subsector of the transportation economy. But we don't, for example, model out how those decisions would have affected other aspects of the economy, like labor, like their relationship with getting materials for their steel and aluminum and that sort of thing. And so if we were to represent that in a CGE model, we could have done that, but we would have had to make sacrifices about how much detail we could get into with like the automaker decision-making piece of it, right? And so that's the trade-off that you're making with these partial equilibrium models compared to the CGE models, right? Right, if you're asking about, why don't we all just do CGE models to represent this stuff, it's because that level of, there's only so much complexity that you're going to be able to represent in a CGE model. Okay, and then there's a couple of different examples of partial equilibrium models here that you guys are welcome to look into if you're interested. Questions? Okay. The next one that I'm going to talk about are optimization models. So a lot of the system level optimization models, so these essentially leverage that optimization approach that we talked about, where we're trying to minimize or maximize something. So usually you're getting some like best set of technology, and usually we're talking about minimizing costs to do that. And this is where oftentimes we're combining like detailed bottom-up models with more maybe simplified macroeconomics. So there's, I would say, a lot of the system models, especially in the sort of energy domain, leverage optimization of some kind in order to, produce their outputs and forecasts and that sort of thing. So there's a particular set of famous models or pretty well-known models. So Markal and Times. Who's heard of Markal and Times? Anyone? Okay. Yeah, and so if you're doing like economy-wide energy modeling, these two are some of the more well-known in the energy sector. So the market and allocation model, Markal, this was first developed by the International Energy Agency. And now maybe a little bit more defunct. They took the Markal model and added a bunch of extra things and improvements to produce the integrated Markal EFOM system, also known as the Times model. And so Markal kind of evolved into Times. And then there's a number of other sort of energy systems models. Message is one that's decently well known by IASA, which is the International Institute for Applied Systems Analysis over in, I think they're based out in Vienna. So this is the model for energy supply strategy alternatives and their general impact, a different type of optimization model. Times and Message have a lot of things in common. And then I chose kind of a random like dispatch and investment model for electricity markets in Europe called DIME. These days there is, for electricity modeling, like PI-PSA is a pretty well-known one in the electricity sector. It's also an optimization model that does dispatch and new capacity. Just to give folks a sense of what the Times model does, and I'm providing this diagram also as a way to sort of generally show what a lot of the sort of optimization models in the same flavor as Times do. So they divide these into kind of supply side modules and demand side modules. And essentially you have different ways of producing energy supply. And so these are all of our primary energy. They go through, a lot of it's going to go through this power generation module, which helps to translate and connect the fuels piece of it with the demand piece for electricity. And so on the right-hand side, you have a bunch of end-use technologies, which may have different sort of demands. And you have a bunch of different service demands kind of on the right-hand side that are based on the end-use technologies. And so it's basically like, here's a bunch of ways that I have to produce the types of energy you want, and then here's all the energy needs that I have based on particular services and technologies. And the optimization says, okay, now fulfill all of my needs based on the lowest cost, and or on particular carbon constraints if you want them, right? And so Yeah, one of the unfortunate things about this class, which I've like constantly trying to navigate, is that, you know, when we go from our small like Kaya type models up to, you know, these types of models, which are much more commonly in use, it would take like the entire class to just the entire quarter just to train people how to use this. Right? It took me like a year to figure out how to run times. Yeah, and so I can really only show you guys kind of these system diagrams and discuss kind of qualitatively how it works, right? But I think the important principle is that we're kind of combining our knowledge about the individual technologies, which we covered at the beginning of class, and then all of the like methodological approaches, right? And the decision-making piece and the optimization piece, that all kind of combines with a lot of work into something like this. And so times is like a particular flavor of these larger energy systems models. But a lot of those system models are going to look like this in some way, right? There's a whole bunch of assumptions that you have to make, you know, in any one of these modules. That's kind of what makes a sort of model unique. But one of the nice things is that, you know, we do have a handful of different energy systems models, and you can try and line them up and see, you know, based on the model structure and assumptions inherent to the model, whether or not putting similar inputs will give you similar outputs. And in fact, there are entire, I don't want to say like fields or disciplines, but there's like conferences and workshops and meetings that are like focused on that. The one that I would say is most relevant to this stuff is the Energy Modeling Forum called EMF, which is held annually by Stanford. And they have, over the years, evolved to create this set of like standardized inputs that you can put into many systems models. And then they have these conferences where they just like compare if the models are giving similar answers, and then and if not, like why, because that gives a lot of insight into important pieces of what are the important pieces of the model. Okay. These things are not totally standalone, right? A lot of partial equilibrium models will actually, you know, try and combine with like optimization approaches, right? And so, yeah, there's ways in which I might take my social accounting matrix and then optimize with a particular sector of an economy. And so not only am I doing these sort of different modeling approaches and combining them, but also kind of combining top-down and bottom-up models. All right, the last one we're going to talk about are simulation models. These are models that replicate many of the rules that describe associations and interrelationships amongst different pieces of your system. And the nice thing about this is with some of the simulation models that I'm describing, you don't necessarily have to follow like a cost minimizing pattern. Normally that, you know, we often think of optimization models that do cost minimization as a way of producing the most efficient outcomes. But at the same time, we also need to be aware that cost minimization doesn't always happen, right? And so the best way that you can represent that oftentimes is by trying to do these sort of simulation models. And there's a whole list of examples of simulation models. But actually the one that I want to focus on is the National Energy Modeling System, or NEMS. And that's built by the Energy Information Administration, EIA. So who's used the annual energy outlook before? Anyone? Okay, a couple people, right? And so this is a really nice resource that you can use from the EIA that gives all sorts of information on like forecasts for different technologies and prices and fuel uses and emissions and basically anything you can think of that relates to the energy system. And NEMS, or the National Energy Modeling System, is inherently a giant sort of simulation model with a bunch of different modules that kind of all integrate into one. And so that for the EIA, this is kind of a schematic at the highest level of the NEMS model. And you can see what the modules kind of break down into. So you have the supply piece, you have a renewables module, coal market module, natural gas market module, and so on. There's a whole piece on the conversion that will have an electricity market module, fuels module, and then on the demand side, little modules for each of these things, for residential, commercial, transportation, and industrial. So these are all the demands by end-use sectors. And just to give a sense of kind of how detailed this ends up looking, right? So if I zoom in onto the transportation demand module, it's got these sub-modules. So within NEMS, so it's got this transportation module, which actually will feed into a couple of the other modules. There's a piece on light duty, on air travel, on freight, and all of this adds up to the energy demands and then an emissions calculation, right? And if I dive even deeper into this, if I focus on like the light duty module, there's a whole bunch of pieces of this that break down into like different regional pieces. There's a vehicle choice model here, the fleet components, and then how they're doing accounting of the stock and turnover of vehicles. And then even more, if I zoom in right onto the technology choice piece, there's this whole sort of logic model piece here that this basically describes, and actually in relation to even some policy levers, there's a like cafe model in here. Yeah, and so you can see we're like zooming in, zooming in, zooming in. NEMS is basically comprised of these sub-modules that are essentially simulations of, based on a set of assumptions that correspond to these sub-modules kind of at the end of the day. Okay? So highly detailed model that gives, at the high level, information about all of this stuff and how it's integrated together. Okay, so to kind of end on talking about our top-down versus bottom-up models, what are some strengths and weaknesses of each, right? Top-down, this is nice because it endogenizes everything together with better consistency. A lot of the times what the bottom-up piece misses are like feedback effects and macro effects that a particular thing might have on your economy and on larger sort of structural changes. Unless you build a bottom-up model that literally accounts for all of these things, like NEMS does, for example, you might miss some of the things that are particularly salient in a top-down model. However, with top-down, you're often lacking details at the technological level. A lot of the outputs are sort of generalized, and so you might not be able to say something about how technological progress or change may be affecting some of these outputs. Because these are often looking at particular economic effects, non-monetary issues and factors that might be specific to some policies or technologies are going to be harder to represent in a top-down model. With bottom-up, we can incorporate a lot of those details of specific technologies, and then provide detailed evaluations at that like finer resolution level. But I will say one difficult part of this is that it is really heavily dependent on like very narrow data requirements oftentimes that might have to do with your specific technology and costs associated with this technology, which can make bottom-up difficult to put together without the right data. Okay, and so that is our summary of top-down versus bottom-up. Although remember the sort of caveat being that there are a lot of these models that have hybridized versions where we're using elements of top-down and bottom-up. So it's not always sort of black and white that one model is totally top-down and one model is totally bottom-up. In fact, many of the examples that I showed have certain elements of the other, which they try and take advantage of. So that is it for today. Remember that homework 2 due at the end of the day, so hopefully you guys have gotten started on that. And otherwise, if no more questions, I'll see you guys on Wednesday.
Homework 3 will be assigned Wednesday too, right?
Yes.